Hi, like you said, my name is Greg, and this talk is about the Ceph distributed storage system. I have been a Ceph core developer for about, 4.5 years now, and I work at Inktank, which provides support for Ceph and is the primary corporate sponsor. We're going to get into storage for the cloud, but let's start off very quickly by talking about the history of storage more generally. In the depths of time, humans saw rocks and they banged them together to make marks. And if you were really advanced, then maybe you had some kind of pigment that you could paint on it with. And that was how you had permanent storage. If you wanted to see what had been stored, you went and you stared at the rock and you said, oh, those marks mean that this is the law about what happens when you poke someone's eye out. Then we got ink and things like papyrus or paper, which we could write on and then read back. And that let us create not just monuments for dead kings or public codes of laws, but great stuff like business records. And many years later, we created computers, and we talked to the computers, and the computers stored things for us on some kind of tape. That brings us about halfway up along this wavy storage picture. And then something funny happened. Before we had computers, and for a little while after we did, the amount of stuff that we stored was mostly based on how long it took to do the storage. A person was directly involved in all of it. You had to sit there and bang on the chisel, or paint with your finger, or write on, or make marks on the papyrus, or write with your pen, or type on the keyboard. And so, because a person was directly involved, then if we could store stuff faster, we stored more. But since no one wants to spend their entire life doing data storage, if a project required too much data to be feasible, then we just didn't do the project. After computers, storage got a lot cheaper, and we created computer programs that could not just respond to people making data, but could look at data and make data of their own and do something useful with it. So now humans are out of the loop, and we can and are creating data in ways where the data creation drives storage systems instead of the storage system driving the data that we create. The cloud is the ultimate incarnation of that. Users will create data as fast as you let them, and they will do so unpredictably. That means your storage system needs to be truly scalable in terms of cost, deployment, and architecture. Let's look at some traditional storage systems first in terms of cost. The standard simple scenario is fine. A computer talks to a disk, and a human gets information out of the computer. You can even add more storage space up to a point by just sticking more disks behind a computer in a RAID, or remembering what kind of data you have on which disks. But for any non-trivial storage system, you don't want one user, you want lots of users. Then you've got several people accessing the same storage, and they all need to route through one computer. That works okay for 3 people in a small office, but not so much for 30. And you can forget trying to get them all to agree about which disk they're supposed to be storing what kinds of data on, or which disk they get to use, or whatever else. Of course, this problem is much worse for a cloud than it is for an office storage server. So what you really want is for there to be a different sort of layer between the human and the storage. So the human or his computer agent just asks for data, and then the request goes to the right place, and you don't need to worry about it. In usual practice, that comes down to some storage appliance which internalizes a bunch of disks and some compute hardware for managing the requests and changing the data. And then people talk to that storage appliance. So that's nice and convenient because your storage is just a box and you plug it in and then people connect to it. But there's this. And that means that when you want to expand your storage, you don't get to lever the economies of scale or the fact that disks have gotten cheaper and computers gotten way cheaper or anything else like that. If you don't want to do all the storage management, you can't even shop around for a different box that you just plug in. You have to buy from the exact same company as you did the last time and probably buy the same product line so that they work together and you don't have to be like, oh, all our data from before 2014 is on this box and everything from afterwards is on this box. So you just spend another $14 bazillion when you need another 10% of storage, even though you just bought another 100%. That closed box combination of proprietary hardware, proprietary software, and proprietary support really doesn't scale very well for the cloud. Second, you want a scalable deployment technique. Your initial deployment of a closed box system, wow, there's even more people. Your initial deployment of a closed box system is just the box and everybody talks to it. When you outgrow that box, you buy another whole box and you plug it into the first box. And when you outgrow those 2 boxes, you plug in a third. Now that is incremental, but it's either very frequent or a really large increment with a lot of capital expenses. And you'll notice that usually your storage bandwidth doesn't go up at just the total amount of storage you have. And finally, you want a scalable architecture so that you can grow from your 50 terabyte proof of concept cloud up to a private or public cloud measured in petabytes. Most of those boxes say something like, we scale horizontally up to 20 nodes. and that doesn't count. And neither does anything where you're like, oh yes, we scaled to 20 nodes worth of storage, but you're going to have 10 gigabits per second worth of bandwidth the entire time. As you've guessed by now, Ceph answers all of these problems. Of course, there are lots of other things out in the world that promise magical unicorn horns and pixie dust. So I'm going to start off with just a brief thing about why you might pay attention to Ceph out of all that stuff. And I should tell you that the last time I practiced this talk, it came out a little short, so feel free to ask questions at any time, and if you're premature, I'll just tell you so. So Ceph. First of all, Ceph is not a project by one guy on the internet somewhere with long, shaggy hair. There's a serious research about how to build a cloud storage system behind Ceph, and we've had the time to turn that research from a demo into a real project, into a real product, because it was started before cloud storage was a thing. Ceph was initially developed as a long-term research project at the UC Santa Cruz Storage Systems Research Center, trying to develop a successor to the Lustre high-performance computing file system that is in use at the national labs. Today, most of the developers are employed by Inktank, which makes money as a services and support provider. Second, ticks the checkbox features you need in a big storage system with a few different object interfaces, a block interface, and a file system interface. And it has all the magic words you would ask for. Let me talk about those words a little bit. When I say that Ceph is scalable, I mean that it is designed to run on petabytes and exabytes of disk. When I say that it's distributed, I mean that it runs on lots of servers, however many you care to put together, on a local area network. When I say that it's software-based, I mean that you take whatever hardware you want and you run the Ceph storage system daemons on it, and they aggregate into a single unified Ceph cluster. And when I say that Ceph is designed for failure, I mean that Ceph deals with hardware failures natively. It replicates all the data in the system according to policies that you set, and then when something fails, it automatically re-replicates that data elsewhere to provide the durability guarantees that you have asked for. Third, and in particular interest to all of you at scale, Ceph is open source, and we mean open source, not just open core. We are a true open source project which does not practice copyright assignment. We do all of our development in public repositories, and while Inktank produces the vast majority of code right now, we have external contributors who provide real value and who are increasing as a proportion of the project. There are already a bunch of different companies which provide various training and support services around Ceph. We have integration with third-party platforms that is maintained entirely by third parties, by different third parties, and our core code has been and is modified by external developers. Ceph is not going to be relicensed after people have become dependent on it. Fourth, Ceph is accepted. We've learned from the failures of Lustre and other cool, nifty projects that lived off in the side. I won't say there are no kinks, but Ceph is everywhere and it has clients everywhere. You won't be stuck on a particular kernel vendor that your provider has validated with their special set of proprietary patches, and it slots right into your normal infrastructure management tools. Finally, Ceph is designed to be easy to use for administrators. Our founder started a web hosting company that learned a lot of painful lessons about the cost of storage and how much manually managing the placement and repair of that storage sucks. Ceph benefited both from that and from the experience of national labs learning similar lessons in HPC scale clusters. That it is hard to both manage the total raw storage in terms of the disks, and that it is hard to partition that amount of storage into working sets that you can actually deal with. So let's go back over the scalability story. Ceph starts with bog standard commodity hardware from whatever company you want. Then you run the free and open source Ceph software daemons on that hardware, and you can buy an enterprise support and management subscription from Inktank, but that contract is totally optional. So Ceph has a much more scalable cost story for cloud storage than closed boxes you buy from one company. The deployment story is similarly scalable. With Ceph, you start out with your commodity storage servers plugged into a regular Ethernet fabric. Then you can, when you say, oh, I need a little bit more storage, and you can add one server, and then you can add another, or you can add two at a time, or you can add a whole chunk of them, whenever you feel like it. And your storage system gets more bandwidth as well as more disk every time you do so. And of course you want a scalable architecture, and the rest of this talk is going to tell you about how Ceph's architecture is scalable. Here we have all the major systems components you can have in a standard Ceph storage cluster. The one at the bottom of the stack is our custom object store called RADOS, short for Reliable Autonomic Distributed Object Store. You talk to this object store using our librados using our librados library, and with that we built our RESTful RADOS gateway object service, our RADOS block device, and our Ceph distributed file system. We'll start with RADOS, because it's the base of all the other systems. So when RADOS was being designed, as I said, for Santa Cruz, the research project, the end goal was to create an infinitely scalable file system. This has a few implications. First of all, the object store itself needs to be infinitely scalable because it's going to be storing all the data. Second, that object store should be optimized for handling files as used in HPC. Large objects on the order of megabytes, not small objects on the order of bytes. Attempting to scale forever has some ripple effects. First, we can't have single points of failure because you want your cluster to be available all the time. Second, we want all of our processes to be distributed because otherwise your resource requirements will eventually exceed what a single node can provide, no matter how beefy that node is. Third, as a philosophical point, we should let users take advantage of the CPUs that our storage nodes provide. Those nodes exist, they're not free, and they're conveniently co-located with data. So when they came onto the scene and they looked at this, then they said, okay, let's look at object stores today. Generically, there are some data storage nodes, which in Ceph we refer to as object storage devices, or OSDs. Many object stores have a master controller node, which handles a bunch of different tasks related to placing data on the storage nodes and keeping track of where it lives. Most of those object stores have a flat namespace you can place objects into. S3 calls these buckets, Swift calls them containers, we call them pools. And those are just logical things inside of the store. And then clients come along and they want to look at an object. And depending on the object store, one of several different things can happen. Either they can ask the master for an object, and the controller goes and gets it for them and says, here's what you asked for. Or they might say, where does the object stored? And the master tells them, and then the client goes and grabs it. Or maybe there is no master, and the client just magically knows where to find the object and does so on their own. That's the approach that Ceph takes. The original way of finding objects in a store with the master controller is to maintain an index of where each object is located. And on every access, you do a lookup in that index. That has nice features. You can balance new and old nodes easily by saying, oh, all new writes go to the new nodes, and in the background we'll move cold data around so that nodes are being used equally. And the master controller is really easy to program to be like, okay, I have these things on these different switches and these things on the same power, and so I need any redundancy that I'm providing the data to cross those failure domains. But it's a single lookup table that you have to be able to scale somehow, and so for large object stores it eventually fails. The new way, the magic I mentioned earlier, is to hash each object, generally based on the name, and to place the object on a node derived from the hash. But you pay a heavy price for that. If you add new nodes to the cluster, then the hash for lots and lots of the objects suddenly says, oh, I live over there. And it's hard to, and so you move lots of the data, much more than the amount that you've added. And it's hard to implement durability policies like place each of 4 different copies on a different rack. We've developed an algorithm called Crush, which fixes those problems. Adding 10% to your cluster moves about 10% of your data. And even better, Crush understands the cluster topology and uses that when making placement decisions so that you can survive the loss of any arbitrary thing you care to survive the loss of, whether that's a core router or a power supply or whatever. That means that you can use some very sophisticated placement policies with Crush. You can make sure each data replica is in a different rack, or you can implement more advanced rules like I'm saying, I want 2 copies in different racks in data center 1, and then a 3rd copy over in data center 2. Or you can take advantage of different types of storage to say, I want my first copy of a piece of data to live on SSDs, and I want extra copies on hard drives. Now, as I've just started talking about replication of the data, and the reason for that is that in a cloud storage system, you need more than 1 copy of your data, or eventually you have so many nodes that you're guaranteed to lose some. We don't want controller. There are a couple of different options for doing replication. We don't want controller nodes for all the reasons we've already talked about in terms of scalability, so they're out. There are systems which have the clients do the replication where they say, okay, I have this object that I want to store in 3 different places, so I'm going to send it to place 1, and then place 2, and then place 3. But it makes writes pretty expensive for the client. So in Ceph and in RADOS, we have the OSDs do their own replication. With that, the client sends data to one OSD, which we refer to as the primary, and the primary is responsible for copying the data to its replica OSDs. We chose OSD replication because it moves the problem of data consistency from the clients to the OSDs, where we believe it should be, in case, for instance, the client goes away after sending off 1 copy of the data. The RADOS cluster intelligently figures out whether the data write actually finished or not. And OSDs often have more back-end network bandwidth than the clients do. It's important to realize upfront that different OSDs are the primary for different data, and that there are different groupings for different data. So the client might have done one write to this guy who sent it to his replicas, and then his next write might go to this other OSD node with, oh look, one of his replicas was the primary last time. For a read, the primary simply sends the data to the client without bothering its replicas at all. So the RADOS cluster has two pieces of software. The most important is the object storage daemon, which we've been talking about. It's a very intelligent bit of code which takes responsibility for all the data it's storing locally, and for moving that data or replicating that data to anybody else who should have it, for moving it to a different primary node if responsibility changes, for directly servicing client reads and writes, and for whatever else happens to the data. Usually, although you run one OSD per disk, and then the server is an OSD node. The OSDs figure out where that data goes using crush, just like the clients do. It's the exact same calculation, and those calculations drive all of that movement and replication activity. We also have monitor nodes, and note that these are monitors, not masters or controllers. The monitor's only job is to keep track of what OSDs there are in the cluster, where they live, and whether they're up or down. And with that, they regularly publish what's called an OSD map, saying what nodes exist. And that OSD map is one of the inputs to the crush algorithm that lets you calculate where data goes. Of course, at scale, some of your nodes are going to fail. So when one does, the nodes it shares data with will notice that it's failed and tell the monitor, and the monitor issues a new OSD map saying, node 17 has died. Then the remaining OSDs work together and re-replicate the data that was on node 17 to restore the durability guarantees that you've asked for. Crucially, OSDs go through the same process for all map changes, whether it's OSD 17 has died, or we've added OSDs 100 through 150, or, oh, this administrator's asked to decommission OSDs 1 through 20. During this peering process, the primary makes sure it knows about all the data in the cluster that it's responsible for. Not that it has it, but that it knows about it and where it is. It checks in with the monitor and says, I am responsible for all this data and I know about it. And then it starts servicing clients immediately. It continues recovery to get all the data where it's supposed to be in the background without interrupting service for any long process like resilvering. As a visual example, we're going to say here we got a cluster with 5 OSDs in it, and the third OSD has crashed. Oh no. The OSDs that it's sharing data with have gone to the monitor and said OSD 3 has died, and a new map has been issued. So let's pretend that each OSD previously had 4 PGs. Normally it would be much larger, but 100 is hard to draw. And we're going to look at the PGs from the first OSD as an example. The first OSD has now gotten the new map from the monitor and is processing it, and it says, okay, I have a black PG, and before it was replicated on the 5th OSD, and now it is still replicated to the 5th OSD, so I don't need to do anything. And the lavender PG was replicated to the 4th OSD, and it still is, so I don't need to do anything. And the blue OSD, or the blue PG, is replicated to the 2nd OSD, and it still is, so I don't need to do anything. But the purple PG was replicated to OSD 3, and it does not. It goes to OSD 4, so I need to send the data to OSD 4. So the OSD 1 will incrementally push all of the data in the purple PG to the 4th OSD. Of course, when an OSD dies, each one that remains is doing that same calculation to push all the data across. So the whole cluster is replicating the data in parallel. And that means that recovery happens a lot faster than it does in a RAID-style arrangement where you have mirror pairs. Because when the OSD dies, someone brings on a new one, and then you wait for a while. To reiterate, this OSD self-management is all powered by Crush, which lets the OSD determine what data goes where without needing to bombard the monitors or any other central lookup service with requests for where its data belongs. You programmatically take an object's name, you hash it into a placement group, which is just a shard of the pool, the logical namespace the data lives in, and then you run that placement group through the crush algorithm with the OSD map to pick the OSDs that the data goes to. So in a RADOS cluster, we have OSDs, which hold all the data and are responsible for keeping it safe. We have the monitors, which keep track of the OSDs in the cluster in a safe fashion. And we have clients, who talk directly to the OSDs and read and write the objects. Notice, remember, very important, the monitors are not in the data path between OSDs and clients. Also notice that because our data placement is rule-based and the cluster automatically handles the changes, administrators do not have to get involved in moving any data when you add storage nodes. It all happens according to flexible rules you've set up, and it happens without any human intervention besides turning on the storage nodes. Ceph is not just scalable for the computers, it's scalable for your storage admin team. So that's RADOS and its architecture. But we haven't talked about what its interface model is for users. For actually using RADOS, we have the librados library, which is written in C++ with bindings for a bunch of other languages, and is a very rich API. librados is not at all like S3 or other object APIs you might be familiar with. You can do file-like operations on the objects that include overwriting part of the object in addition to just appending or replacing it. Objects support xadders and have an associated key value map. librados supports single object transactions where you can say, I want to read this data, and then depending on the value I get out, I want to do a write or maybe I don't. It has a locking primitive called watch notify that lets you set up watches on an object and then push data to everyone else who's watching it. And it lets you, and librados lets you inject your own code that will do whatever you can make C++ do to the object. And we use, that's what we call object classes, and we use those extensively in our internally developed applications. We envision other people using object classes to do things like generate thumbnails of images online in the data path, or encrypting and decrypting data in place, or supporting specialized data formats like HDF5 on the node. Finally, RADOS supports very powerful snapshotting mechanisms on the object, which are all based on copy on write. So, yes? An object is a serialization point, so they are serialized on the OSD, which is primary for them. Yeah. So if you want to use librados, you write an application that links to it, and then librados handles all of the cluster connection, configuration, and communication nonsense using boring old TCP/IP. We have customers who are actually using librados directly, and we've used it ourselves to build two great services. The first of these is what we call the RADOS Gateway. The RADOS Gateway is built as an Apache plugin right now, although we're making it standalone as I speak, and provides a RESTful S3-like service which is backed by RADOS. The gateway uses a pretty large subset of the librados features in order to provide an S3 and Swift API compatible object store, which is suitable for exposing to the world in a public cloud. To use it, you would write an app or take an existing one for S3 or Swift. You would point it at a RADOS gateway or a cluster of them. You send REST requests to put or get an object, and the gateway turns that into the correct librados calls. Hooray! This is a real product which is used to power DreamHost DreamObjects offering, as well as a bunch of other people I can't talk about. And you can drop it into an OpenStack install in place of Swift. As with the rest of Ceph, you can scale the RADOS gateway by running multiple instances against one cluster to get more bandwidth, and they will remain coherent with each other. Cooler still is the RADOS block device. RBD is a fairly thin layer on top of librados, and it projects a block device out over objects across the cluster. So as the person running the block device accesses it, RBD turns those requests into reads and writes to much smaller RADOS objects. Because it's already a distributed network block device, migrating VMs which are hosted on RBD is really easy. There's no disk data to move, so you just have to transfer the in-memory state. Of course, in the cloud, you don't want to host one virtual machine, you want to host thousands. So I think that asking how to spin up lots of machines at once is one of the true tests of a cloud storage service. RBD is thin provisioned, and the whole scheme makes it really easy to clone instantly. You pick one RBD volume as your golden image, this one here, for instance, and then when you want to make a clone, you just generate a header for each of them. And you'll see that it's not yet using up any extra storage space, but when you turn on one of your clones, and then on writes, the clone will write to new objects, only taking up as much space as is required. In this example, we've got 4 extra blocks which have been touched. And reads will go to the clones block if it exists, or fall through to the parent if not. The RADOS block device is integrated into lots of projects, and it's getting added to more all the time. It's upstream in the Linux kernel, so you can use it with physical machines as well as with virtual hosts, and it's supported in QEMU and all of its associated hypervisors. And of course, RBD is supported by many, many cloud systems. Just to pick 2, OpenStack speaks RBD natively throughout the project. Cinder, Glance, and Nova all cooperate to use its thin provisioning and cloning features correctly. And you can use the RADOS gateway in the same place you would ordinarily use Swift. CloudStack also can use RBD for both primary and secondary storage. Hooray! So, Up until this point, everything I've told you exists today and is supported by both the community and by Inktank commercially. After this, we're talking about the future. First up is stuff that is in our Firefly release, which had feature freeze earlier this week and should be available in about a month. There are two major features I want to talk about. The first is what we call cache pools. These pools work like a durable write-back cache. You can create a cache pool called foo for the regular pool bar, and then whenever you had an access that would have gone to bar, you send it to foo instead. It's the job of the OSD storing pool foo to handle pulling data into the cache on demand, and for flushing dirty data and removing cooler objects when the cache gets full. The most obvious use case here is to have all SSD storage caching accesses to regular hard drives, but we expect users to come up with other scenarios as well. Just to visualize that, I've illustrated a write here. You have a client, and he says, oh, I want to write an object, and it goes to the OSD storing pool foo on the bottom. And they just take the write, and then they return to the client as normal. And then at some later time, when the client is or is not doing something else to different objects, then the primary in pool foo says, okay, I'm now pushing this cold data out to the cold storage tier, which it might be somewhere else. A read would go in the opposite direction. The primary OSD in the cache pool gets asked for the object, and either it says, oh, I have it, and it serves it up right away, or it goes out and fetches it inline from the cold storage pool and serves the data to the client directly. The second major feature is that the use of erasure coding instead of replication for your data durability and reliability. Previously, we made all data durable by replicating it. A client would write a 4 megabyte object to the cluster, and the cluster would then store a bunch of copies of that 4 megabyte object in different storage nodes for a total of, in this case, 12 megabytes of storage actually used. With erasure coding, instead of copying the data wholesale, you carve it up into a configurable number of pieces and then build parity blocks which would let you recover from the loss of other groups of blocks. So on a 4 megabyte object write, the cluster might, in this example, store 4 1 megabyte pieces plus 2 1 megabyte parity chunks. This example is what's called a 4-2 read Solomon erasure code. So there's 4 blocks of real data and 2 blocks of parity. And it has a 50% overhead, 6 megabytes of storage, and can survive the failure of 2 storage nodes. But the exact numbers of data and parity blocks are actually configurable by the administrator. And our erasure coding algorithms are pluggable for more advanced users. Looking out a little farther in the future, RBD and RADOS, RBD and the RADOS gateway are our primary cloud offerings right now, but the Ceph distributed file system is coming up. ceph-fs sits on top of librados and provides a POSIX file system interface to users. I should say right now that we're still in the future part of the talk. Unlike RBD and the RADOS gateway, ceph-fs is not yet considered ready for general production use. But the code is available to play with, and we've recently started refocusing on it at Inktank, so here's a teaser. ceph-fs stores its data in the RADOS objects and its metadata as well. All metadata updates are sent to special metadata servers, or MDSs. Unlike in most file systems, you can have any number of these MDSs. These MDSs do not have a hard tie to any particular piece of metadata, and you need to provision them based on how much activity your file system has, not based on how much data it has. In order to scale properly, ceph-fs automatically partitions the metadata load across different MDSs. Visually, we have this starting file system hierarchy on one MDS. Here the gray boxes are blocks and the white ones are files. As we add new metadata servers, the servers split up the tree based on how busy it is, not based on absolute size. And that actually extends to having a single very busy directory being split up across multiple MDS nodes. This is called dynamic subtree partitioning, and it carries a lot of administrative benefits over static partitioning like you would do with most storage boxes. Instead of a storage admin needing to manually move data around to balance the node, and maybe actually moving the data as well as the metadata work, the servers do it themselves on a regular basis to maintain peak performance based on the load that's happening right now at this very instant. Also notice that this lets you scale your metadata performance and your total storage, throughput, and size independently of each other. This is all made possible by original research and by building an intelligent consumer of the RADOS object store instead of treating the metadata handling as a legacy part of your cloud system, which many people do right now. Because of some careful work in the implementation, the ceph-mds cluster supports a couple of extra features beyond POSIX that are pretty cool. The first is that we have snapshots in the file system. And these snapshots are of arbitrary subtrees, not just of the entire tree or of a particular volume or whatever. You go into a folder that you want to snapshot, you do a makedir on a hidden.snap directory inside, so you would do makedir .snap/1, and then you have a stable copy on write snapshot of everything that is in the current directory and all directories underneath it. So you could use that to take a snapshot of the entire file system hierarchy from the root, or you could take a snapshot of a single user/home directory in order to do offsite backups, or the user could take snapshots of their documents folder to provide local comparison and rollback capabilities. This is all implemented using copy on write, so snapshots don't take up any extra space until you start changing the data which has been snapshotted. Second, ceph-mds implements what we call recursive accounting for directory sizes and other metadata. So you can see who's using up your cluster space quickly and cheaply. Normally, if you go into a file system and you run an ls-l on a folder, then it says, oh, I'm 4 kilobytes, because that's the amount of block space it takes up. In ceph-mds, it says, oh, I am 3.6 gigabytes, because that's the size of all files which are stored underneath me. And you can also take advantage of the different storage strategies in RADOS from within ceph-mds using a virtual xheader interface that says, okay, I want the data to be stored in this pool, and I want it to be chunked up and striped in these ways. So in one pool, you could have in one cluster, one ceph-mds unified namespace, you could have one slow pool with big objects, which is where all your Hadoop workload data goes, and a fast pool with little objects for Scratch, and a slow pool with small objects for user home directories, or anything else that you need to have in your system. You can put it in there under that single tree. So that's a short intro to Ceph, and I'm sure that you want to know how you can use it. There's lots of help available from the Ceph website, ceph.com, including quick start docs and public help hours. If the idea of reading documentation or going to public mailing lists or IRC doesn't appeal to you, you can get paid help for production or proof of concept clusters at inktank.com. And if you do, you will not be alone. This is a partial list of groups and product offerings publicly making use of the Ceph technology. This is not complete, and there are a lot of people who are actually using Ceph privately or without even talking to Inktank in any way, shape, or form.